Everyone, you've been reading your workbook and your textbook on vectors and scalars, so it'll just be a very brief introduction on vectors, and then we're going to look at the addition of vectors and subtraction of vectors. So just then on vectors, remember that vectors have a magnitude and a direction. Magnitude and direction, that's vectors, whereas scalars just have a number. Scalars just a magnitude, just a number. For example, let's have a look at some of these. Scalars, mass, just a number, 2 kilograms. Length, just the length, 1.3 meters. A distance, again 4.6 kilometers. Speed, no direction. Power, energy, work. Vectors, examples of vectors. Displacement. So displacement, I've started here and I've ended up there. This is the displacement. It's got a length that was 2.4 kilometers, and it's in this direction here, which is about 50 degrees east of north. So displacement, it's got a length and it's got a direction. Velocity is the same. I could be heading home from school on my bicycle, and I can be going at some point, I can be going at 50 kilometers per hour. Might be a bit of an exaggeration, and I might be going west. So my velocity has got a size and a direction. Acceleration, again, force, newtons in a particular direction. So our vectors have got a direction and a size. Here's 5 examples to look at. Is this a scalar or a vector? The rugby player is running 10 kilometers per hour towards the touchline. Is it a scalar or a vector? It's a vector because it represents a magnitude, 10 kilometers per hour, in a direction towards the touchline. So this vector represents the velocity of the rugby player. 2, the volume of the box at the west side of the building is 14 cubic meters. That's a pretty big box. Is this a scalar or a vector? It's got a size, 14 cubic meters, and it's got some sense of a direction, but it's a scalar. It might be a bit tricky as it gives the location of the box at the west side of the building, but this has got nothing to do with the direction of the volume, which has simply got a magnitude of 14 cubic meters. So volume is scalar. The temperature of the room is 15 degrees. Scalar or vector? To scalar, because there's no direction, it's just 15 degrees. It's not 15 degrees up or left, it's simply 15 degrees Celsius. The car accelerated north at a rate of 4 meters per second squared. This is a vector because it's got a direction, north, and a magnitude, 4 meters per second. We also know that acceleration is a vector quantity. And our notation for vectors is this. So if we have a vector A, we have A squiggle. Another vector B squiggle. Here's our notation for vectors. They have this tilde sign underneath it. Later on when we talk force, we'll talk about force. It's a vector. Our acceleration we might have as a vector. Velocity we might have as a vector. Displacement a vector, etc. So now we want to look at is addition of vectors. Addition of vectors. Let's have a look. When we add vectors, we tend to draw them. For example, here is a vector A, and here's a vector B. And they might be displacement. Someone walks this distance here. They walk this distance. A little time later, they walk this distance. So we've got 2 vectors, A and B, representing 2 displacements. And if we add these vectors, we add them head to tail. Here's the head. The head has got the arrow on it. The tail we leave empty. Tail. and head. The way we add vectors is tail to head. So let's add a plus b. Let's write this vector a plus vector b is equal to, let's have a look, a plus b, a plus b is equal to, if we were to consider this as displacement, if we start out here, we travel to here, to this point, then we travel to this point, overall we've gone this distance here. This is our overall displacement, and we'll write that this here is a plus b, and we'll call that the resultant. The resultant a plus b. We add our vectors head to tail, and when we describe this resultant vector, we'll give it a length, so it'll have a magnitude, and it will also have a direction. So in this case we might say that is 65 degrees from here to here. So it's got a magnitude and it's got a direction. For example, here's Selwyn College here, and I've got myself a little drone, and my little drone initially, and it's quite a powerful one, quite a big one, I initially fly it over to Kelly Tarleton's undersea world, which my grandson really loves. So initially we can say it's got a displacement which we can represent with this vector here. That is our initial vector A, and that's from Selwyn to Kelly Tarleton's. And then I thought, well, I'm going to fly it over to St Heliers Beach to have a look over there. I've got my HD video camera on it, so I fly it over here, and it doesn't matter how I wiggle. We're not interested in the distance we travel, we're interested in where it's displaced to. And now we've displaced it over here to St Heliers Bay, so our second displacement from Kelly Tarleton's is here. So this is B, the vector B, displacement B, and that's from Kelly Tarleton to St Heliers Bay Beach. And we want to know what is A plus B, what is the total displacement my little drone has done, and we add the vectors head to tail. Displacement vector A, displacement vector B, they add up together to be from tail to the final head. This is the resultant vector at this particular angle, and we can see that is A plus B. We add our vectors head to tail. We can also look at our vectors. Let's look at another vector. We're going to look now at flying our drone from Selwyn College. Now, Selwyn College. I'm going to fly it now directly north. So it's going to go directly north here at around 50 kilometers per hour. 50 kilometers per hour. At the same time, there's a wind blowing from west to east, and it's blowing at 20 kilometers per hour. A wind blowing at 20 kilometers per hour. So we've got our vector 1, our velocity vector 1, and our velocity vector 2. And we want to know what there will be the result of adding vector 1 to vector 2. We go head to tail, and we say therefore the resultant vector A plus B we can draw from here, This is the resultant vector, and that will be about, so that's about 53 kilometers per hour at this particular direction. Addition of vectors a plus b, a plus b is equal to the resultant, which we usually have two arrows, heads in the middle of it, and that's our resultant vector. Subtracting vectors. First of all, I'd like to look at subtracting bananas. Let's look at it mathematically. I started with 6 bananas and ended up with 4 bananas. What I want to do is I want to do 6 minus 4 bananas is equal to 2 bananas. Now mathematically we can write this another way. We can write 6 plus negative 4. 6 plus negative 4 equals 2. Now we're going to use this for subtracting vectors, because when we're looking at the vectors with magnitude and direction, it starts to look a little bit complicated, but by the end of this you'll see it's actually really quite straightforward. Remembering that 6 minus 4 is the same as 6 plus negative 4 is equal to 2. So let's then have a look at our vectors. Let's look at 2 vectors, vector A in this direction and vector B in this direction. And we know how to add vectors. We know how to add A plus B. A plus B is equal to A plus B. But subtraction, how do we subtract? Remember our bananas, 6 minus 4 is the same as 6 plus negative 4. Well, let's have a look at subtracting A minus B. A minus B. First thing we need to know, we're going to say that's equal to A plus negative B. First thing we need to know is, if this is B, what is negative B? Negative B is a vector exactly the same length but in the opposite direction. So again, if this is our vector A, what is negative A? It's a vector of the same length but in the opposite direction. So if we're going to subtract B from A, what we're going to do is add negative B. So A minus B is A plus the negative of B. So let's do this then. A plus the negative of B. That was our B, and this is our negative B. So a result of that is this vector here, adding head to tail, and the resultant is from the first tail to the final head, A minus B. Let's think of an example again of our, well, it's actually my drone. My drone is flying north at 40 kilometers per hour. And I want to subtract from it 30 kilometers per hour heading towards the east. So our drone is flying north at 40 kilometers per hour, and I want to subtract from it this vector here, 30 kilometers per hour. So I want to go my 40 vector minus my 30 vector is going to be the same as my 40 vector plus the negative of 30. This is our 30 kilometers per hour vector, so this is going to be negative 30. So what do we get when we add 40 plus negative 30? 40 plus our negative 30, and our resultant is going to be this, which, as we know from our Pythagoras, is going to be 50 kilometers per hour. So we can say 40 kilometers per hour vector in this direction minus 30 kilometer per hour vector in this direction is equivalent to 40 kilometers per hour this direction plus negative 30 kilometers per hour in this direction, a resultant of this here. Let me just repeat that if we want to subtract a vector a minus b, it's equivalent to a plus the negative of b, where if this is b, vector b, the negative of b is exactly the same length but in the opposite direction. So if whatever vector we have, we simply need to swap the arrow around to the other end to end up with the negative vector. I'm going to bring back my bananas now to look at something else. We're going to look at change of vectors, and we're going to say that we started with 6 bananas. So initially our bananas we've got final bananas, and we want to be able to calculate what is the change of bananas. How do we work this out? Change of bananas. Normally we would say the final number of bananas minus the initial number of bananas is equal to the change of bananas. Remember, that's our change of symbol, change of bananas. How do we work out the change of bananas? We have the final number of bananas, subtract the initial number, the final number, subtract the initial number. Now in our case we've got the final number is 4 minus 6 is equal to minus 2. The change of bananas is minus 2. Well, that makes sense. We've lost 2. We can also write this as we've just done before. 4 plus negative 6 is equal to negative 2. And we're going to use this for our change of vector. So we're going to say the final vector minus the initial vector is equal to the change in that particular vector. And we'll look at a couple of examples. We're going back to our drone and we're starting again at Selwyn College, a very good place to start. And we're going to fly our drone now from the school up to Mission Bay, the far end of Mission Bay, near the fountain. So our initial displacement is from here to here. So that's our initial displacement. And then we're going to fly this now. We're going to fly it to the far end of Kauai Beach where the sailing club is. So our final displacement is here. Our final displacement. And we want to be able to calculate the change of displacement. What is the change of displacement? So let's use our formula over here for change of displacement. For change of displacement we go final displacement minus initial displacement is equal to the change of displacement. And we will rewrite that as final displacement plus the negative of the initial displacement is equal to the change in displacement. So let's have a look at this then. Our final displacement final displacement plus the negative of the initial displacement. Here is the initial displacement. Here then must be the negative of the initial displacement. So final displacement plus the negative of the initial displacement, final displacement plus the negative of the initial displacement, and we can then say this resultant must represent the change of displacement. And we can actually rewrite this in a way that will convince us it's true. If we have the final displacement has got to be equal to, take this to the other side, add initial displacement to both sides, we end up with initial displacement just the change of displacement. Doesn't that make sense? The final displacement has got to be the initial displacement plus the change of displacement, which is what we've got here. If we have the initial displacement plus that change of displacement, we'll end up with the final displacement. So if we want to find the change in a vector, we have the final vector minus the initial vector, and we'll rewrite that as final vector plus the negative of the initial vector. We can look at a particular example. We can look at velocity. Here it is, we've got our little motor car. It's got Snoopy and Woodstock in it, and initially it's travelling at a velocity of 4 meters per second. That's our initial velocity, and a little while later it's travelling in this direction at 3 meters per second. And we want to ask the question, what is the change of velocity? What is the change of velocity? And our formula that we looked at before, the change of velocity is equal to the final velocity plus the negative of the initial velocity. So let's look at how fast Snoopy's going afterwards. Well, what's the change in velocity? Remember, final velocity 3 meters per second in this direction plus the negative of the initial velocity. This is the initial velocity. This then must be the negative of the initial velocity, 4 meters per second in this direction. So change of velocity is this plus this, this plus this. This then must represent the change of velocity. Change of velocity. We'll look briefly at just one further example. I played cricket a little bit when I was a boy. I wasn't very good at it. I couldn't bowl and I couldn't bat. I could run great distances and pick the ball up and throw it back, but I couldn't play the rest. But supposing you've got a cricket ball being bowled at 20 meters per second and it meets with a bat, something which I was not very accomplished at doing. It meets the bat and then it bounces off the bat, travelling at 40 meters per second in this direction here. So this is our initial velocity and this is our final velocity. What's the change of velocity of the ball when it hits the bat? What is the change of velocity of the ball when it hits the bat? It's equal to the final velocity minus the initial velocity. Just as we did with bananas, the change of bananas is the final number of bananas minus the initial number of bananas. The change of velocity is the final velocity minus the initial velocity. And we're going to rewrite that final velocity plus the negative of the initial velocity. So let's see what that looks like graphically. Here's our initial velocity. Negative of the initial velocity is the same length going in the opposite direction. How do we add vectors together? We add them head to tail. Let's add final velocity plus negative initial velocity, and we end up with this here representing the change in velocity. Now the next video we're going to look at worked examples, some specific worked examples from what we've been looking at today, looking at our vectors, addition of vectors, subtraction of vectors, and then finally we were just looking at changes in vectors, change of velocity, change of force, etc. So that's it. See you later. Whoops, I said see you later, but what I mean is that in the meantime you should be looking in blend space at vectors and choose from tiles number 1 to 8 and be looking at those. Thanks.